this one we're looking at what's out there, galaxies, and other cool stuff. Our solar system is the sun and the planets orbiting around, and that is in a thing called a galaxy. And our galaxy is called the Milky Way.
Right.
And the reason is because if you see it in the night sky, like this picture here, it's this kind of murky, milky, cloudy looking path across the sky.
Yeah.
And hence Milky Way,
Right.
because it's a kind of a milky looking.
Yeah, it's milky looking
path.
in terms of like that cloudy whitishness. The thing is that you can't actually see that here in Toronto because of the light pollution.
Yeah, the last time you could see it from Toronto was during the power failure in 2003.
Right, in 2003, right, because it was pitch black. There was no light. But if you're ever out camping and you're in the complete darkness and you look up, you will actually see that band going across the sky.
Yeah.
And that's actually part of, or one of the arms of the galaxy.
Yeah, so you'll see in a moment what the galaxy looks like, because there we are. That's what our galaxy, what the Milky Way galaxy would look like if you could see it from...
way up high.
Yeah, from above.
Yeah.
It's a big flat disk with kind of a bulgy thing in the middle.
Yeah.
And that milky path is when you're looking through the plane of the galaxy.
Right. So it's just looking, if you're looking at the edge.
Yeah.
As you
It's
go.
like you're inside a pancake.
Yeah.
Right? So
and you're
can
looking towards the edge. of the
if you look through the pancake, the pancake sitting flat on the table, you're looking side to side. You see lots and lots of pancake. If you look up and down,
you don't.
the pancake's very thin, so you can see out of it. So the Milky Way part that we see in the sky is looking in the plane of that disk.
Right. Now, nobody's actually ever taken a picture of this. These are all artists' ideas.
Yeah, trying to map the Milky Way is difficult. It's like trying to map Toronto from inside an apartment building in downtown.
Yeah.
Right. Just looking out across Toronto and then trying to figure out where everything is.
Right.
It's not easy, but
it's doable.
It's by someone.
Difficult.
People with very powerful computers and lots of time on their hands.
Yeah.
So our galaxy is about 100,000 light years across. And in terms of spacing of the stars, just to give you an idea, imagine the sun is like a grain of salt. And then you want to make a galaxy by sort of basically spreading out grains of salt. Well, those individual grains of salt would have to be about 10 kilometers apart. So it's almost entirely empty space.
Right.
Only in the core is there like a whole bunch of stars.
Right. So
kind of bunched up together.
It's almost like a super gigantic version of when we talked about the atom and saying, okay, if Toronto was an atom, then your nucleus would be the size of a basketball.
Right.
Well, now if we say a galaxy is the size of a grain of salt, well, the next nearest galaxy is way over here.
Or the stars within the galaxy.
Yeah. Sorry. Yeah, the stars within it. That's right.
Yeah. So it's very, very spread out. In the core of the galaxy, it might be closer. They might be, maybe half a kilometer apart or so.
Yeah, if you have them all bunched together.
Some cool things about galaxies. In the middle of most galaxies, and it may be all galaxies, we haven't quite figured that out yet.
We haven't looked at them all.
They contain something called a supermassive black hole.
Right.
And this is an object that is millions or even billions of times as heavy as the sun. And it's so compact, it has no volume, right? It's all of that mass, but basically compressed to a single mathematical point.
Yeah.
And the gravity is so strong that even light can't escape.
Right.
That's what it's called.
And that's the thing, though. The thing you got to realize is that a black hole is not a hole; it's an actual thing.
But it kind of makes a hole in space.
Yeah.
Because once you go in, there is no coming out.
Right.
So, some of the cool things about these supermassive black holes is that because they basically, they act like a drain plug, like a drain.
Yeah.
Stuff
Everything swirls
in.
down. Yeah.
But as stuff spirals in, it's accelerating to such high speeds, it's becoming super duper hot that it releases X-rays and high energy particles and all kinds of stuff, and it shoots jets out sideways. Now this is like extreme physics.
Yeah.
But it's cool, and some of the galaxies you can actually see these.
Yeah, you can see it as a because it's matter super accelerated to just under the speed of light.
Yeah.
And you actually see beams coming out of the galaxy.
Yeah.
Now, unfortunately, if you're in the path of that beam,
you get kind of fried.
Yeah.
Now, weird things. These really, really big black holes, we don't know which came first. Like, we don't know whether the black holes formed at the center of the galaxies from the stars collapsing. What we'll see in a couple of lessons where black holes come from. But basically, when a massive star dies, its core can become a black hole.
Collapses.
And we don't know whether black holes formed in the center of galaxies and then just kind of all sunk to the middle and then started eating each other and growing to a supermassive black hole, or whether there was massive black holes to start with and the galaxies
they sucked the stuff in.
kind of formed around them.
Right. Yeah,
it's still an active area of research.
Yeah.
And
a very cool area of research. The funny thing is that, how do you see a black hole?
They're building a device, an interferometer, that they're hoping to actually get images of the silhouette of the black hole at the center of our galaxy by 2015.
Wow, that's pretty close.
So that would be pretty cool.
Just a couple years.
More weird and extreme physics, stuff called dark matter. Which some of you may have heard of because it sounds all very weird and mysterious.
And it shows up in sci-fi shows and crazy stuff like that.
Star Trek. It comes up in Star Trek.
Well, Star Trek was red matter in the movie.
Oh, the red matter.
Don't even want to go there.
Yeah. The stuff we can see, right? We can see stars and planets and dust and gases and all that kind of stuff, right? Because it gets warm and it glows and it reflects light and it produces light and so on.
Right.
But there's also strong evidence of stuff that we can't see. And what this came from was that they looked at these spiral galaxies that are rotating, and they realized that they're rotating too fast. Like at the speed at which they're rotating, they should basically be flying apart.
Right.
And so they.
It's kind of like sorry to interrupt. It's kind of like if you take a pizza and spin it too much, it gets thinner and thinner and thinner, and poof, flies apart.
Have you done that?
Not lately. I have done it once.
So there had to be either our math was wrong,
right,
or there's something else there making more gravity.
Yeah.
And so
the problem is you can't see it.
Well, and this is the problem. So there's more and more evidence that there's something wrong.
Yeah.
Either there's something else there that we can't see that's making more gravity, or our understanding of gravity is completely wrong.
Right.
But one of the other things is that there's something called gravitational lensing, and gravity can actually bend light if you've got enough of it.
Right.
So if you've got
but we're talking a huge amount here.
Yeah.
We're not talking the gravity of just a star.
No.
We're talking massive.
Right. And so if you've got a really large mass, whether it's an entire galaxy or a galaxy cluster, you can see this lensing where the gravity actually bends the light around it. And this is an image of a galaxy cluster. So all of these galaxies are part of a cluster. They're all sort of gravitationally bound together. These curves are not kind of smudges on the film. Those curves are actually galaxies that are behind that are the light from them is being bent by this cluster of galaxies. Yeah. But the bending is too much to be done by just what you can see.
Right.
So there has to be something more there, is what it boils down to. And we still don't know exactly what it is.
But this is a pretty good explanation.
Yeah. And whatever it is, there's about 5 or 6 times as much dark matter that we can't see in the universe as there is visible matter.
So there's actually more stuff we can't see than what we can.
Exactly.
Yeah.
Exactly. And that is, our best explanation now is it's some kind of like subatomic particle that just doesn't interact with anything else, right? So it doesn't.
Light just doesn't actually come off of it.
Light doesn't come off it. It doesn't reflect light. It doesn't produce light. It's just kind of there, and it interacts with gravity, but with nothing else. And so physicists like to come up with clever acronyms, so they call it weakly interacting massive particles, or WIMPs.
For short.
And that's one of the things they're looking for at the Large Hadron Collider.
Right.
Yeah, so they're trying to see if there's anything, any of these particles or anything like this that might be produced.
Yeah.
They're also trying to build detectors that might detect the 1 in a quintillion collision that might occur.
Right. Yeah, because these things don't happen all that often in terms of...
Well, yeah,
Well, I mean, it does happen a lot, but if you're talking about the size of the universe...
Yeah.
You know.
So the object would be, I mean, these particles, they don't interact, so they would just pass right through the Earth without just right through without interacting with anything.
Right, yeah.
And so once in a while, they might smack into something on its way, and if so, it might release some energy. And so there's detectors that are trying to do that, but it's hard. Okay, the shapes of galaxies. They come in a variety of shapes, and we can kind of group them. So we've got these sort of spirally galaxies that just kind of look like spirals.
Water going down the drain.
Yeah,
kind of look.
yeah. And then there's spirals that have rather than a circular center, they've got kind of a long, skinny middle,
right?
Which is referred to as a bar, right? Like a.
Again, scientists not being original sometimes when it comes to names go, it looks like this, so we'll call it that. At least they didn't name it after somebody like biologists would. Oh yeah, biologists name everything after people.
Yeah, so they'd probably call this like a Schneider galaxy or something. Anyway, so there's barred spirals and spiral galaxies, and then these ones that look like great big footballs, and those are called elliptical galaxies, again, because they're ellipses. The elliptical galaxies tend to be much, much bigger, and so it's thought that those might result from multiple smaller galaxies kind of merging, becoming one great big thing. There's also some other shapes. Either they're small galaxies that aren't quite big enough to make one of those spirals, or if they're two galaxies colliding, they make weird shapes. So down here...
This is your interstellar car crash.
Exactly. And that car crash and the forces involved and the gravity and the magnetic fields and everything causes all kinds of weirdness to happen.
Throwing stars.
So even though, remember we said that those grains of salt were like 10 kilometers apart.
Right.
So the actual stars don't collide. They just kind of pass right through each other. Right. But because of the gravity, the galaxies get all kind of shredded and so on. And so these are just called irregular galaxies, which is a good sort of description.
Doesn't fit either of the three, so it's irregular.
Right. This is the Whirlpool galaxy. So there's a spiral galaxy, and it's interacting with this smaller galaxy.
And it almost looks like it's sucking it down, just like a whirlpool.
Yeah.
Again, scientists not being original with their names.
So galaxies come in big groups called clusters. And then the clusters in turn can form things called superclusters.
A cluster of clusters.
A cluster of clusters, which is pretty cool. And this is the Virgo star cluster that we mentioned that in the distances. The Virgo star cluster, and that's about 50 million light years away.
And you can see all the little
galaxies, right? So there's a couple of elliptical galaxies here and a couple of spiral galaxies in there as well. And then way off in space, this is the Hubble Deep Field, where the Hubble telescope basically looked at one point in space for like a month straight or something. In this whole picture, I think there's only two stars. This one over here is a star.
And one right above our heads.
This one's over here is a star. Everything else in this picture is a galaxy.
Right.
So all of these little dots are all galaxies.
But like you say, it took a month to see that, because if you just looked at it, what you would see would be just black. You might see those two stars. So like we were saying, it takes a long time to see this because they're very, very far away. And
very, very faint light, So it's like with a camera, right? When it gets dark, the pictures come out shaky because the shutter stays open longer. Well, this shutter's open for like a month or two at a time. Yeah.
Luckily, with the space telescope, we could actually keep it still and point it in the right direction.
Right. Okay, so some other things. Star clusters. Okay, so there's a couple different kinds of star clusters. Within the galaxy, when stars form, and we'll talk about star formation later, but when most stars form, they form these big clouds that kind of collapse and produce multiple stars together, right?
You get it like a glob.
Yeah, it's like a litter of puppies, right? You get a bunch of them all at once.
But then, of course.
And so they start off together, and then eventually they tend to drift apart. But these are called open clusters because they tend to be fairly loose associations of stars. Right. And our sun was probably part of a cluster like that at one time.
But kind of just
over the 4.5 billion years of our sun, that they kind of spread out. And so one of the actually areas of research is people are looking for our siblings, right? Our brother and sister.
What cluster did we come from? Where all the other stars came from?
So this is an open cluster. It's called M39, and so all of these bright stars form together at about the same time from the same cloud of gas.
But they've spread out over time.
Right, and eventually they will completely drift apart. And this is the Pleiades, which you can see naked eye. You can usually see 6 or so of these brighter stars with the unaided eye, and from a dark sight you can see 8 or 9. I've known people who have seen 11. 11, but from a dark sight, yeah.
Wow. Because usually most people only see about 5 or so in the Pleiades constellation.
It looks kind of like a little version of the Dipper.
Yeah.
It's fairly small. When you see it in the night sky, it looks kind of like a little fuzzball until you look at it.
You can look at it closer.
Look at it closely.
Pull them apart a little.
Beautiful in binoculars. But it will be up in the fall.
Oh, it's below the horizon now, so we're not going to see it.
It's setting just after sunset now, so you won't really see it now. Okay, so then there's another type of cluster called a globular cluster, and that's almost like a mini galaxy. It's globular because it's a globe, it's a ball, right? And they're all gravitationally attached. They don't drift apart, and those tend to form kind of in the outside of the galaxy, and they kind of buzz around the galaxy like little swarms of bees.
Oh, yes.
So there's a picture of one of these globular clusters. So this ball of stars here, this one has somewhere about 500,000 stars, all gravitationally interacting and kind of holding each other.
Not enough to be a galaxy, but...
Right. It's kind of like it's a little mini satellite galaxy.
Yeah, it's the difference between, say, like a planet and a moon kind of idea. It's just a smaller kind of version.
Yeah, kind of. There's also these things called nebulas. And nebula means cloud. It's Latin for cloud. And there's many types, so just kind of going through quickly. Ones like this, pointing at the screen.
Look at the screen. Yeah.
There are these giant gas clouds, clouds of gas and dust that are collapsing and forming stars.
And the glow is from light reflecting off of that dust and gas.
Yeah,
and that sort of stuff. So it's not actually glowing. It's just some of it might be.
Some of it is. So there's kind of 2 ways that it can happen. One is that the light can bounce off. But the other is the
heat, the pressure.
The heat and the pressure, but what's kind of cool has happened is ultraviolet light that's given off by the stars can kind of energize the gas, and then the gas itself then glows.
Oh wait,
back.
we saw this in chemistry with Bohr's
so
electricity, the excited electrons.
Right, so excited electrons. When the ultraviolet light hits these things, the gases get excited and they re-release gas, and so they glow with their own color, which is different than the color of the stars.
Right.
Okay. So where are we here? This one, the nebula here is the same color as the stars because that's reflecting the starlight. Whereas here, it's glowing red because it's the color that hydrogen glows when it's
the gas is mostly hydrogen
by ultraviolet.
And we kind of mentioned this in the chemistry, and it's like we can't run out and grab a sample of this. We have to use the light to figure out what it is.
Yeah, but since each element has its own kind of colors that it produces when it's excited, we can look at these things and see, it's this color hydrogen. Red, so it's hydrogen. There are these things that are called planetary nebulas, which is kind of a misnomer because it really has nothing to do with planets.
No.
The reason it's called planetary is because when you first see it with a telescope, it looks. So when you look at a planet, you can see the disk of the planet,
right?
Whereas a star just looks like a dot.
Yes. Right.
And so when you look at something like this through a telescope, it looks like a faint disk, like almost like a ghost of a planet.
Right, it's kind of like that ring that you see in the center of the screen there.
Right, and so it looks like there's something there, but it's not as bright as a planet, but it's not a point like a planet. Right. So that's why they were called planetary nebulas, because it was a nebula that looked kind of like a planet.
Ah, yes.
And these are formed from dying stars. And again, when we talk about the life cycle of stars in a couple of lessons, we'll show how that happens. And then there's stars that die in more violent ways when they blow themselves to pieces in a supernova. And that makes something like this. This is a remnant of a supernova. So there was, I don't know, 1,000 years or so ago.
I was to say, was this the one that was visible in China? There's one that was visible around 11 something, 14 something.
Yeah, there was one that formed the Crab Nebula.
That's the one, the Crab Nebula.
Yeah.
And it was even so bright it was visible during the daytime.
During the daytime, yeah. Which is proof. Anyway, so when these stars blow themselves to bits, they send the pieces all over everywhere, and that gas is still highly energized. So we see this kind of remains of an explosion that happened a long, long time ago as the stuff drifts out into space. And
eventually, some of this stuff will actually potentially form new stars.
Yeah, this gas can combine with other gases and form new clouds of gas that can then reform new stars.
And the ultimate in recycling.
Yeah. I think that's the last slide.
I believe so, yes.
So, bye.
Bye-bye.